So to start us off, we imagine we look at objects in the world, as Paul was just telling us, and those objects elicit color experiences, or qualia. And the question of qualia inversion is the idea that maybe the experience I have when I look at an apple is the experience someone else has when they look at a leaf. That there may be a disjoint between which stimuli we're looking at and which experiences we have. And the typical conception of this possible philosophical problem stems from the fact that you can imagine looking at an apple, light bounces off the apple into your eye, and it activates these three different photoreceptor types that you have in your eye to a different degree. So the apple is going to stimulate the L cone, which roughly corresponds to the red cone, to a large degree. And then somehow the activation of these cone types gets converted into a color space, where the differences between the colors is somehow represented by the position in this three-dimensional space. And what this sort of representation leads to is the idea that, well, maybe for different people, you can have L cone activation leading, instead of to red, to them having a green experience. So that would be a red-green inversion, but you can imagine all sorts of other changes where you could have any sort of rotation or inversion of the space. I should flag, even at this stage though, that it's not as simple as just imagining that color space is definitely a three-dimensional color space represented by a sphere. I should also mention that there are known physiological variants. So obviously we've heard about colorblind people where they can be missing these cones or have dramatic differences in their sensitivity. But even in normal people, you can have slight changes in the sensitivity of these cones. So the specific nanometer, that's the peak excitation, can be slightly different for different people. Also, we talk about the 3D space as representing the position and the relative similarities or differences of colors. But I should note that when you ask people, you get different results about what the space should look like depending on whether you're discriminating between colors or asking for similarities between colors or asking people to categorize colors. And all of these things together lead to concerns that, like, well, maybe it's not really as simple as a three-dimensional Euclidean space. But that doesn't really matter. The concern is still that for different people, different stimuli might be eliciting different experiences in the most general sense. So considering colors and the relationships between colors leads one to consider whether qualia have structural properties or relational properties or not. So one idea is that the structural properties or relational properties of qualia are totally irrelevant. So the phenomenal character, the redness of red, is fully transparent, it's non-relational, it's non-extrinsic, it has nothing to do with other experiences that one could be having. Other views, though, hold that there might be something intrinsic and relational. So the redness of red is somehow also dependent on its relationship to other colors. Or at least there's some level of structure that's present in a red experience as well. And there are people who've explored this sort of approach, such as Andrew Lee with his objective phenomenology ideas. Then there's also people who posit that qualia or experiences are entirely relational. So the phenomenal character, the redness of red, has nothing intrinsic to it, and it's entirely determined by the other relationships that a person could be having. So this is the idea of phenomenal holism. So this is just to point out that there's varying views on whether or not there's relational or structural properties to qualia. That being said, if you're interested, if you're interested in the relationships of qualia and the relationships between them, how do you actually go about measuring these sorts of things? So in a practical sense, what we would do is we show people stimuli, get those stimuli to elicit experiences in a subject, ask them how similar they are to each other, and if you do this systematically, you can end up with these sets of similarity relationships between stimuli definitely, and arguably also between the experiences or the qualia that they elicit. And when you start thinking about the relationships in this way, a whole bunch of different ideas or problems can become a little bit clearer. So to make that more explicit, if we imagine some typical person, we can imagine them looking at a set of stimuli, and those stimuli elicit a set of experiences or qualia, and you can position those by their relative similarities to each other. And then you can describe that with this sort of dissimilarity matrix, where dissimilarity is just the inverse of similarity. So 0 is the most similar, the objects to themselves, the experiences to themselves, and the apple is most different from green, so it's the most dissimilar from green. So the first thing we can imagine is someone who has some sort of rotation where the relationships between the stimuli and the relationships between the qualia that those stimuli elicit is rotated. So previously, the pink, the purple, and the blue were all very similar to each other, and the orange and the yellow were more further apart. And now if you rotate the space, it's the red and the orange and the yellow have become more similar to each other, and now the blue and purple are more different from each other compared to before. And this is a kind of detectable change. So we could see this if we asked people and we obtained their similarity reports. But then there's other kinds of inversions or relabeling we can imagine, which is the more traditional kind where the relationships between the stimuli all stay the same. It's just that the experiences or the qualia elicited by those stimuli that are changing. And in this circumstance, you have exactly the same dissimilarity relationships, exactly the same relationships between the stimuli. It's only the stimuli to the experiences that have changed. And also, then obviously, the relationships between the qualia themselves have changed. So the pink and purple are now more different to each other than before. So there's a whole set of different possibilities we can imagine. So we have our typical person. We can imagine a typical person, but with a slightly different set of dissimilarity relationships between their experiences and their the stimuli that they see. And even just in this circumstance, there's then the question, according to particular views, as to whether one person's red is still exactly the same as the other person's red. They're being elicited by the same stimuli, but now they have a different structure to them slightly. Then there's the case of the detectable inversion. So the relationships between the stimuli change, and the stimuli to experience relationship has changed. This sort of thing we could go looking for. And then there's the undetectable invert or relabeling case, which is the one that is most concerning because we can't ever hope to find it. And my talk, sadly, I can't answer all of the questions, but I can at least talk about whether there's any evidence for the detectable invert or the typical variant being present in actual psychological experiments that we can run. So to talk about the actual experiment that I performed, so I took a set of 93 colors, and they formed 4,371 unique color pairs. Take about 500 participants. This is doing online experiments, which makes getting larger samples a bit easier. And we show each participant a subset of all the possible color pairs. So in this circumstance, it's not that each participant has described the dissimilarity between every single possible color pair. We ask them to give a numerical dissimilarity rating. So 0 is the most similar, 7 the most dissimilar. And then I took the participants, divided them randomly into two groups, and aggregated their judgments together for those two groups. So I took the mean response for each color pair across all of the participants within each group. To give you an idea of what the actual online experiment kind of looked like, it's very simple. I would just show them a screen, briefly show them two stimuli, and then ask them to rate the dissimilarity between the two stimuli. So this is the results that we get at the end, after we've collected all the data and excluded the bad participants. And you can see here that the patterns of dissimilarities between the two groups look pretty similar, but they're not exactly the same in terms of their responses. And the first question that we wanted to know is if we take away the labels, and even if we re-index the matrix, the dissimilarity matrix, is there something about the structures that we can use to still accurately identify which color on which structure corresponds to which color on the other structure, according to the original labels? We can do this for red or for green or all sorts of different things. The idea being that if we can do this, then that at least makes it plausible on a structural account that the red for group A is the same as the red for group B. And if we can't do this, even to begin with, then the structural approach isn't going to work at all. So the idea we had in mind was to do something similar to what's been done previously for unsupervised alignment for things like languages. So imagine you have two languages with two sets of vocabulary, and you have no idea how to translate from one language to the other language. all you know is something like the similarities between words in those languages. So something like word to deck. You can use tools to, without having any idea of what the labels are, align the two structures together and come up with your best match between words in one language and words in the other. And the specific technique that we used was this idea of Gromov-Wasserstein optimal transport, where basically the idea is for each set that you have, so imagine for each language or each set of colors, you can look at for each point in that set, so each word or each color, the distance from an object in one set to all of the other objects in that same set, and you can try and match it with an object in the other set that best matches those relationships. And of course, there's a very large number of possible ways to do that matching, so possible transportation plans, but you're trying to find the transportation plan that minimizes the error, or that has the best transport plan. And using this, we had two goals. So the first one was to find the label correspondence for the transportation plan with the minimal Gromov-Wasserstein distance. So for the plan that works best, that has the lowest error, does that give us the correct correspondence according to the original labeling scheme? So we wanted to assess the accuracy of that solution. And then the other goal we had in mind is thinking about the possible inversion cases that we thought about at the start. So imagining color space as a three-dimensional space. If we perform some rotation, or if we perform some inversion along particular axes, how well did those solutions perform compared to the original labeling? And I'll describe that in a little bit more detail as I go as to exactly how that worked. So the first point, how well does the optimal solution work? So we found that the optimal solution works pretty well. So just looking at the structures alone, without considering the color labels, we were able to get an 81% roughly correspondence between which colors were seen by group A and which colors were seen by group B. And you can see when this does make errors, it makes errors that are pretty, between colors that are very similar to each other, as you can see here. So it's understandable that these colors can get confused with each other according to this sort of scheme. The second thing that we then did was to try and assess the possible inversions. And to describe this in a bit of detail, so on the left is a three-dimensional representation of the aggregated dissimilarity judgments between participants, plotted using multi-dimensional scaling in a three-dimensional space. So this isn't according to their positions, according to traditional ideas of color space like C-Lab. This is just based on the dissimilarity judgments that the participants gave us themselves. And we can take this 3D representation and we can look at it also in 2 dimensions. And what originally we were trying to do is to see whether these points in group 1 or group A could be accurately identified with the points in group B or group 2 here, based on the relationships between all the points. But when we're considering a case of inversion, what we're considering is taking this group B, so one of the 2 groups, and either performing some sort of reflection or rotation where we rotate the relationships, and where originally we were trying to find the optimal transportation plan when we were identifying a color in group A with a color in group B that had the same original labels. Now we're doing it where we're identifying a color in group A with a different color in group B, according to this sort of rotation. So what we were trying to find before was red to red. Now we're trying to find how well does red to green work. Does it still have the same sort of error when we look at the Gromov-Wasserstein distance, or does it have a much larger error? Do the structures not fit together so well? So yeah, what would the Gromov-Wasserstein distance be for this kind of label correspondence, and how does it compare to the original labeling scheme? And so what we found with what we've done so far is we haven't found any evidence that this works particularly well. So that's the Gromov-Wasserstein distance for trying to find the correspondence between group A and group B according to the original labeling scheme. That's the distances that you get when you try just random relabelings from group A to group B. And when we've tried various rotations so far, they've all been much higher in terms of their distance and their error than the original labeling. But I should point out that we've only done a subset of all of the possible enumerations that are possible. You can imagine rotations, you can imagine inversions, but we've only done it based on rotating or inverting the space according to a multi-dimensional scaling idea of how the colors should correspond. But you could do it based on like ideas of the physical properties of the colors. You could do it based on all sorts of other different ways. So this isn't to say that detectable inversions are completely impossible. It's just to say that we haven't already found them with some basic ideas of what would potentially uncover them. And that's all the data from my main experiments, but just to go back to undetectable inversions briefly before coming to the end. I just find the idea, it sort of gives me philosophical vertigo to a certain degree. So positing these ideas would be that there's some way where different people could have different experiences while still looking at the same stimuli that we would never ever be able to detect. And it's worse than that because not only would they necessarily have inversions or rotations, they could also possibly be having completely different or alien experiences. Because if the color properties are just intrinsic instead of relational, then it might not be that their red is my green, it might be that their red is something I could never experience, or it could be C-sharp, or it could be a warm temperature. Who knows? There's no way I've ever detected that. That's not a proof against it, it's just I feel an intuitive argument for the relational approach. Yeah, this could even happen within the same person over time. I talk very fast. But just to summarize briefly, so there's multiple different kinds of conceivable inversions and relabelings. We haven't found any evidence of detectable inversions being plausible so far, but we're going to keep looking for them to see if we can make any of them work. And there's many relevant parameters that we could still be looking at. As I said, undetectable inversions give me vertigo, but that's not real proof that they don't exist. And the ongoing work that we're doing is testing more plausible inversions and relabelings, doing the same kind of experiment, but in a colorblind population, to see whether the structures are the same for those with color anomalous vision or not. And then one other thing that we're trying to do is there are many criticisms of the idea of color space as a three-dimensional color space, and particularly a three-dimensional Euclidean color space. So what I would love to know how to do is to go from the sort of data I've been collecting and in a principled way work out what's the best sort of space that could describe that data, whether it's like a metric space or a non-metric space, what its dimensionality is, that sort of thing. So if you have any ideas on that later, I'd love to hear about them. And in general, also, we're trying to work out, with using these ideas, clarifying what the different philosophical commitments of this sort of approach are. So to finish, I'd just like to acknowledge all the people who helped me with this work, and particularly Masafumi Ozumi and Genji Kawakita, who did a lot of the actual computational analysis for this work. And I'm happy to take any questions.